Hello. Hello.
My mistake. No. Kushmita's father also, Kushmita is also Naha.
Good afternoon, respected faculty members, esteemed alumni, distinguished guests, and dear students. A very warm welcome to the second A.K Saha Memorial Lecture. I, from Purna Banerjee, a second-year undergraduate student of the Department of Geology, feel deeply honored to host this prestigious occasion today. At the outset, I would like to pay my sincere tribute to the remarkable accommodation, visionary scientist and beloved teacher, Professor A.K Saha, whose immense contribution to earth sciences continue to inspire generations of geologists and researchers. His dedication to academic excellence and scientific inquiry remains an enduring legacy for all of us gathered here today. Today's Memorial Lecture stands as a tribute to Professor Saha's extraordinary life, scholarship, and contribution to the geological sciences. It is also an occasion that brings together faculty members, students, alumni, and researchers in celebration of scientific learning and intellectual exchange. To formally begin today's program, I would now request the head of the department and president of Geological Institute, Professor Kolal Halda sir, to kindly come forward and deliver the inaugural address.
Good afternoon, everybody. And I welcome you all to the second annual Professor A.K Saha Memorial Lecture. This lecture series was initiated last year as a part of the centenary celebration of the illustrious teacher and researcher Professor Saha. The lecture was delivered in the first edition by Professor Shoribal Gupta of IIT Kharagpur. This year we are honored to have with us Dr. Vineet Kumar Gahalaut, the director of Wadia Institute of Himalayan Geology, to deliver this lecture. I welcome Dr. Gahalaut on behalf of all associated with the Department of Geology, Presidency University and the Geological Institute. Actually, sometimes I get confused if these two need a separate mention. To give a proper perspective to Dr. Gahalaut, the Department of Geology is the oldest geology teaching institute of India and perhaps also of Asia. And the Geological Institute, which is run and managed by the students of this department, is almost certainly the oldest such body. In the Geological Institute, almost 120 years old now, actually, with some hiatus in the interim. And they organize seminars, they organize workshops, and most importantly, the students publish an annual journal called Bhuvidya, in which majority of the contribution comes from the students themselves. So on this occasion, we extend a very warm welcome to you, Dr. Gahalaut, from the oldest Geology Department and Geological Institute. Thank you very much for taking at least a day off from your extremely busy academic and administrative schedule to come here and deliver the lecture. Thank you.
Thank you, sir. Now, I would like to invite Professor Gautam Bose, sir, to kindly felicitate Dr. Vineet Kumar Gahalaut, sir, with a bouquet and a plug on the special occasion. Thank you, sir. Now I would like to invite President of Geological Institute, Professor Kolan Haldar, sir, to felicitate our esteemed speaker, Dr. Vineet Kumar Gahalaut, sir, with the annual journal of the Geological Institute, Bhuvidya. Thank you, sir. Now I would like to invite Professor Jyoti Mukhopadhyay, sir, to share a few words in remembrance of Professor A.K Saha on this occasion.
It's difficult to talk about Professor A.K Saha within a short span of a few minutes. But I'll try to bring out the person. He is an incomparable teacher and a researcher. And born in 1925, he had a brilliant academic career afterwards, topping the list in all the examinations, BSc and MSc, not only in geology, but amongst all the subjects. So his was the highest marks. And after a brief stint in the Geological Survey of India for about 3 years, and within that short period of time, he made significant contribution on the discovery of sapphirine in the Khashi Hills, and then the significance of sapphirine was not so well known. So much later, the significance of this discovery was appreciated by the geologists. And also he was then associated with the new emerging disciplines of engineering geology and hydrogeology, which were just coming up. These departments are just coming up within the Geological Survey of India, and Dr. Saha was associated with this work. And he was associated with the legendary geologist, Professor Dr. J.B. Auden, and an association which Dr. Saha treasured to the end. And then from 1951, he left Geological Survey of India to join the Presidency College, and till his demise in 1997, he was an integral part of the department. So he taught mineralogy, petrology, and other subjects also. So when he was young, there was nobody to teach sedimentology. So his mentor, Professor S.K. Rai, Santosh Kumar Rai, who was the head of the department at that time, he entrusted Professor Saha to teach sedimentology to the honor students. So Dr. Saha prepared himself to teach sedimentology. Being a hardcore, hard rock geologist, he prepared himself to teach sedimentology to the students. He was not a very flamboyant teacher. He was not a very big orator, but his lectures were full of useful information, the latest advances in the subject, and he tried to inculcate among the students the logical thinking and how to make conclusions from geological facts. That was, so his lecture notes were treasured for generations of students. And he was a devoted researcher, and he had the uncommon ability to divine that what is the frontline area of research in geology. So when he started geology, his research career as a young teacher on the Shingbum granite, then the controversy about whether granites are magmatic or metasomatic, that was the question was that was in the rage. So Dr. Saha came to the conclusion that the Bahalda Road granodiorite, which was his subject of study, that was metasomatic in origin. And then he went to Canada to work with Professor W. Moorhouse, and within a short span of 3 years, he did a phenomenal amount of work. He mapped 3 plutons in Ontario, structural mapping of the plutons, and he came back from Canada a confirmed magmatist. So he had no difficulty in transitioning from the metasomatic origin to magmatic origin. So he was always in the front line. And he, when he came back, he took up a systematic study of the Shingbum granite, which was then just a red blob on the geological map of India. Nobody was very certain what is, apart from the fact that it is a granitic body, nobody knew about what constituted the body, what were the petrological characteristics, what were the mineralogical or structural characteristics, nobody knew. So he took up a very systematic study of the Shingbum granite pluton, and then came up with and he delegated each part of the Shingbum granite was mapped by his students, both at the MSc dissertation level and the PhD doctoral level. In those days, the MSc dissertation was taken up very, very seriously, and many of the old MSc dissertations were contributions to geology, and they found their way to publications in internationally reputed journals. So, and then from this study, systematic study, he came up with a picture about how the pluton was emplaced, what were the different phases of the plutons, and what were the mineralogical and petrological variations within the body. In those days, the petrology, the geochemical studies of the rocks were in its infancy. They were just coming up. Before that, the main tool for study of the igneous rocks was the microscope. So he was, and his mentor, Professor Santosh Rai, was a master in optical microscopy and identification of minerals under the microscope. But Dr. Saha realized that simple petrological microscopical characteristics would not be enough. In the coming days, more and more information would come from the chemical compositions of the rocks. So he set up a geochemical laboratory in the Presidency College against all odds. And Professor Saha had this ability that lack of infrastructure never deterred him from his research. Either he created the facilities in his own institute, maybe in a rudimentary fashion, maybe in not so very advanced, but the instruments with which he could carry out the work. He set up the rapid chemical analysis was the method in those days. So he set up this optical spectrophotometric determination of the minerals. And for the rare earth elements and the trace elements, there was no facilities at the Presidency College, but he got the work done by outside agencies. He had a tremendous reputation in the geological community, so he could influence the powers that be. So his trace element data and rare earth data mostly came from the very advanced laboratory in those days of the Atomic Minerals Division. So, and towards the end of his career, he came to realize that environment is coming to be a big topic of research in the coming days. So he shifted his attention to study of the environment. So he first started a work on the air pollution in urban and rural areas, and he built up the basic instruments for collecting the air and determining the pollutants. And his one big achievement was setting up of the Center of Studies of Man and Environment. And from there, he did many significant project works on environmental aspects of geology, particularly related to the South Bengal delta. But for example, the arsenic pollution, he carried out important work, and water resources and hydrogeological parameters, pollution in the water, pollution in the air. So, he was in Bengali there is a term called Kormobir. So he was not only an academician and a researcher par excellence, he was a Kormobir. So he started a new journal from the Presidency College. The journal of, so that went on for several years, and many important publications were found their way to this journal. Unfortunately, after his demise, this journal is practically discontinued. I don't think it is being published anymore. Shantanu, it's not being published anymore. So that is a sad thing, but perhaps this department can take up the initiative to start thinking about republishing the journal as a mouthpiece of the young researchers of this department and the other educational institutions. He was a very simple, unassuming man, very kind-hearted, but he was a strict disciplinarian. He made his own rules. He lived by those rules himself. He conducted his life according to his rules, and he expected others that others should also follow these rules. So he was very critical of slipshod work, and he was critical of taking these things in a very casual or lackadaisical manner. He would be very severe in his criticism of his students, but he always encouraged the students to do hard work and to make significant conclusions from the data they collected. So I had the privilege to be a student of Professor Saha. So I have seen him on very close quarters as his administrative ability. He headed this department for many years, and during his time, the department changed its face, and from a very sedate department where first-class research was being done to a very modern-looking, with new instruments came during his time. And he was instrumental in getting a mass spectrometer for these departments, which was a great achievement in those days. But it is sad that he left by the time the mass spectrometer came, and this mass spectrometer was never put into use. So, we have a lot to learn from Professor A.K Saha, from his life, from his researches, from his conduct, and how he treated his students and his colleagues. So I pay my deepest respect to him. He's still a beacon to any young researchers of this department and from anywhere in India. Thank you.
Thank you, sir, for your thought-provoking address. It is now my immense privilege and honor to introduce our distinguished speaker for today's memorial lecture, Dr. Vineet Kumar Gahalaut, sir. Dr. Vineet Kumar Gahalaut assumed charges as the director of the Wadia Institute of Himalayan Geology on 23rd January 2025. He is presently on deputation from the CSIR National Geophysical Research Institute, where he has been serving as chief scientist since 1999. Dr. Gahalaut has made exceptional contributions to the field of seismology and tectonics, particularly in understanding crustal deformation and seismic activity in the Indian subcontinent, with special emphasis on the Himalayan region. He also served as the director of the National Center for Seismology from 2015 to 2019. One of his most significant scientific contributions has been the establishment of a large GPS station network across India for monitoring crustal deformation. His pioneering research has greatly advanced our understanding of earthquake processes and tectonic dynamics in various tectonic domains of India. Dr. Gahalaut is the recipient of several prestigious honors and awards, including the Indian National Science Academy Medal for Young Scientist, the CSIR Young Scientist Award, the Ani Talwani Memorial Prize, the M.S. Krishnan Award by the Indian Geophysical Union, and the Physical Research Laboratory Award. He is also an elected Fellow of the Indian Academy of Sciences, the Indian National Science Academy, and National Academy of Sciences, India. We are truly privileged to have such an eminent scientist with us today to deliver the second A.K. Saha Memorial Lecture on the topic Crustal Deformation and Strain Rate of the Indian Plate. Without further delay, I would like to request Dr. Vineet Kumar Gahalaut, sir, to kindly come to the dais and deliver his lecture.
Thank you very much. And first of all, thanks Shantanu for inviting me here. I like to travel, but generally I avoid attending conferences and said then I know that it is coming from I didn't know that Professor Mukhopadhyay and Professor Sadas Gupta would be here. I thought the morning when I learned this, I thought, do I need to check my slides again to make sure things are all right? Uh, Professor Mukhopadhyay, of course, he doesn't remember, and of course, I was very small kid at the time. Uh, the first time when I met him was in 1990 when there was a conference in Kurukshetra University, and that's when I gave my first presentation, and I mean, like he's considered one of the sweetest person and you know during the people of our age, because I don't think I've ever seen him in bad mood or always smiling, always appreciative of everybody's work. One of the sweetest person I have seen in my life. Thank you, sir, both of you, Professor Somnath Gupta and Mukhopadhyay sir, coming here. And thanks everybody for joining me. I hope that uh, I'll make, I'll try to, your my work will will be of some interest to you. I basically work on crustal deformation. So I work on current day, what is happening today, uh, what are its implications on earthquake, what are big processes, and um, the, the other good thing is about this work is it takes me to all exotic places. I love traveling, so it takes me to the most exotic places, which if you go in your lifetime, that would be remarkable. For example, going to Barren Island, which is kind of a prohibited place. So I go to Barren Island. I also go to Antarctica. So that we have a station at Mathri. It also takes me to places like Siachen Base Camp, uh, or Daulat Beg Oldie, or the Galwan Valley. So, and that's also a reason because of which I like it. Of course, this journey started from when I started when I finished my PhD, and then I started working on GPS observations. When I started working on crustal deformation, if you see this particular slide, this particular it's, okay. So there is a C, and that's where my journey started. So these are called GTS pillars. There was a by Survey of India. There was sometime 150 or 200 years back. There was an effort when Britishers were making maps, and they were doing a lot of astronomical observations. And there was a lot of there was some emphasis on looking at deformation which is happening at all these places. So these pillars were erected and connect with Calcutta. So there is a GTS pillar here in Calcutta. I do not know how many of you have seen it. So this is 75 feet tall, which was built in 1831. When now it exists. The only problem is that now it is surrounded by lots of buildings, so I don't think you can actually make observations from it, but it has got its own historical current. So those who have not seen this, please do visit. These are mammoth structures which you see all over India at some selected places, and that's where from my journey started. So I For example, coming back to this, so this is almost like a 6-story tall structure. It doesn't have any way by which you can go up. So we had to put a ladder fabricated, then went on top of it, top of a GPS. That's when my journey actually started. Um, and these are the morning. Somebody was saying Kutch. So these are, of course, these were erected later than Kutch, later than the Allahabad earthquake. But that's when uh, Survey of India, run by Britishers at the time, had this idea that earthquakes cause deformation. The plate tectonics was not hypothesized, elastic rebound theory was not hypothesized, but then there was some idea that the deformation, surface deformation, is caused by earthquake. And 1819 Kutch earthquake was the first one when Allahabad, when it caused Allahabad as almost like a 6 feet, 10 feet tall fault scarp, which was later on mapped by Survey of India. There was a guy called Baker who mapped it using leveling, and that's when the geodetic work in India actually started. Now, why it is important? Of course, at that point of time, it was all about map making. It was all about connectivity, and they were looking at, I mean, rather than going into what was the purpose of those maps, but the whole idea was to connect places so that the transportation becomes easy, whether to carry items from one place to other place, or to for people convenience. So that was the idea. But then slowly we started realizing the importance of these observations, and then we started using them for crustal deformation. And then the idea of using them uh, in seismic hazard assessment, that also came up. But before that, there were several uh, uh, several efforts which were made, which are continuously even now there are. For example, everybody knows about word stress map. It's basically a qualitative map in the form of it only gives you direction as to what is the direction of SH max or principal stress direction, using earthquake focal mechanism, using well breakouts, using that kind of stuff. So that was the first step towards seismic hazard assessment. Word stress map started time in 1889 or even much earlier. Then came the global strain rate map, uh, which started using geodetic data. But then even now, most of the in most of the places, it's mainly confined in the plate bound region because it combines geodetic data uh, from the land part, and then earthquake data from the marine part. So so the map is not that comprehensive. Of course, in some regions like US, the map is very good, but nevertheless, even this effort is going up. Then coming back to Indian subcontinent, Indian region, we do have such maps. For example, the first map, seismic zoning map, which was revised recently, those who are aware, but then it has been rolled back. But again, it only uses it's more like a scalar map, and if not to be quoted, but it's a very primitive map for seismic hazard assessment. But nevertheless, that's a starting point for seismic hazard assessment. You also remember there was an effort which is called GSHAP, Global Seismic Hazard Assessment Program, wherein some quantification was done, some quantification of seismic hazard, some simulations were done. So that's also a map which which is still there, and people still use it, will still upgrade it. Then came from global strain rate map. Then that's the map which we have prepared. That's called strain rate map. So that's the map which you see for for many regions now, especially for places like US, entire US, or for places like where um, Africa is the rift system in Africa. So there's a beautiful strain rate map from that region also. So the problem with all these strain rate map is that uh, we all use GPS data for it. So strain is just a derivative of displacement. So you require accurate GPS data for it. You require huge amount of data, lots of data to generate to prepare strain rate map. Then came a map which is called locking map. Now all these maps which I have showed so far, all of them, they have their plus and minus. All these maps have their own limitations, advantages. But all these maps so far, which I have talked about, all of them, they lack the physical process which causes these earthquakes. So there's not much physics involved in generating these maps, and that's the biggest disadvantage of. And that's why now we have which we call as locking map, in which we use these data, the displacement data or strain rate data, and then we use the concept of plate tectonics, use the concept of elastic rebound theory to see how much a strain is actually taking place on the, in case of Himalaya, main Himalayan thrust, or in subduction main thrust zone, we call MTZ. So we try to look at the extent of locking which is taking place in the convergent plate margin. These maps are, as I said, so these maps are good only for the convergent plate margin, because that's where, unfortunately, I can say so, we think that we understand the earthquake processes. All our earthquake process, we think that they're governed by elastic rebound theory, and hence and accordingly we prepare these maps. Even now, when it comes to intraplate earthquakes, stable continental region earthquakes, we still don't understand as to how the strain accumulates, what is the physical process which takes place to cause strain to generate these intraplate earthquakes. For at least for convergent plate margins, we have a unifying mechanism, elastic rebound theory, which tells you how do you accumulate strain and how do you quantify it. So, but again, locking map also has got its own disadvantages or limitations. Probably I'll come to that a bit later. So, as I said, every map has got its own limitation. So it's not that I can declare that this map is better than that map. Every map, every product has got its own limitation, its own advantages, and we use them depending upon the purpose what we want to explain. In case of intraplate, in case of stable continental region, we still rely on strain rate map, because we still don't understand how earthquakes occur in plate interior region. But in case of convergent plate margin, we switch to locking map, because that's where we think whether we know how do earthquakes occur, and that's why we have these locking map for convergent plate margin. The entire purpose of doing this is the dream, which we never talk about. We don't declare that we are working on earthquake prediction. But the fact is that yes, all of us are working towards earthquake prediction. It's an old, of course, it is considered as out of fashion, old-fashioned word, and the moment you use it in your project which you are funding, I mean, immediately it will be shut down. So it's not a, we don't use this word, but the fact is that all of us, we are working towards earthquake prediction. We are working towards that there will be a day when we will be able to, after understanding these earthquake processes, understanding these earthquakes, we'll be able to predict them. And of course, the new word is hazard mitigation. That fine, we cannot, as of now, we cannot predict earthquake. We cannot do that, but at least we can do some mitigation measures. We would know as to which are the regions where which are more prone to earthquake. We can try to understand the process behind it, behind those the strain accumulation, and then we want to know as to, in case of a big earthquake occurs there, what would be the impact of that earthquake in that region. And that's the most important key here. We cannot predict the earthquake, but if we can predict the impact of it, that becomes that's a product which is sellable. That's a product which people will like, and that's a product which people actually look for. And that's what we are, all of us, we are working. But and then we have problem. And please don't mind if I use some strong words, but that's how things have happened over time. So we started with empirical relations, then computer came, then theoretical. We started establishing theoretical laboratories, observational data. We went into large computations, and of course right now it's all data intensive, AI, ML, things like that. The slide looks beautiful, but when it comes to subject like mine, could be true with that science as well. And this slide certainly does not explain anything. We are still stuck with empirical relations. We still, many of us are still using the same old concept, using limited data, predicting or forecasting or extrapolating it to using empirical relation. It doesn't work. When the entire world was collecting data, when the entire world was establishing observatories, field observatories all over globe, somehow we were sleeping. We were only working with one or two observatories. Those have grown up with me. You submit a project to some funding agency, you ask for 20 observatory, and they give you 5 observatory, right? So I do not know what was going on in the mind of the committee, that something which requires 20 observatory, I mean, what that person will do with those 5 observatory, and the product which you will get from that 5 observation is certainly going to be inaccurate, inexact, and it may not even represent the thing which is going on in that. So somehow we lagged behind. Computational, yes, of course, we started using a lot of computations. Suddenly we started talking about AI, ML. But what will you do if you don't have good database? Your database is weaker. What will you do with your AI, ML? That's especially true, at least in my subject, in earthquake, whether it's GPS or the waveform seismology. A lot of people are talking about AI/ML, but AI/ML requires, machine learning requires huge database. It's all, I mean, a beautiful lecture by in I think so there was a lecture in WIHG INSA annual conference by ISI past director, I forgot his name, from Calcutta. Right. And then he was talking about the AIML. And then he said that, look, the foundation of all this AIML, whatever it is all based on pattern. It's all based on fundamental statistics. So you can use AIML without understanding what it is doing, but actually the foundation starts from there only. So and any product which you develop through AIML, ultimately it will depend on how strong is your database. Statistics of low number, of less number is dangerous. You will always end up in problem. It works best when your database is strong. And that's the reason because of which, people like me who didn't have probably much theoretical idea, knowledge, we started working on data generation. And that's what we got at the end of it. So before this, you are seeing this map now today, but then believe me, if I show you a map 2 years older or 1 year old than this, you will not see many vectors, many vectors inside the latency region. So for this, we used almost like 1600 GPS sites all over India, all over Indian subcontinent, including 65 sites in latency region. And all these 65 sites were actually established by our group, by me. I was involved in all of it. And this is the result of it. So it actually shows how the plate is moving, how which are the places where strain is accumulating, which are the places which are deforming fast, which are deforming slowly. If you look at this map very carefully, you will see that there's hardly any change in length of the vector. So as if the entire plate is moving together without deform. But the moment you come into Himalayan region, then you start seeing the length of the vector is getting slower. So that's where the strain has started accumulating. The deformation has been accumulated in the Himalayan region, and as you go further north, the vector length starts decreasing. At some places, for example, in Indo-Burmizak, it starts rotating, right? And that's what all these plate models, global plate models, they suggest. This is these map. They're not very different from the global plate models, which have been developed by several Westerners. You can do there's it. Many of us, we talk about reference frame, but it's only changed. You see the same vectors, assuming that there's something else which is fixed. So you change the reference frame. So if you for example, if you change the reference frame Indian plate, if you're sitting in the Indian plate and you are seeing the entire world how it is moving. So of course the Himalaya is coming towards you. That's what you know for sure. And look at what is happening here. There's hardly any motion here. This is the size of vector. I'll show you better vector. But there's hardly any motion here, and that's what you expect when you talk about stable continental. It doesn't deform much. By the way, this is all what is happening today. What is happening in last 10 years? Continents do deform on longer time scale, but what I'm talking is last 10 years, last 15 years, or last 20 years. And the way the way it is done is like this. For example, this is data from Hyderabad, GPS station which we established. So this station is running for last 30 years, almost like 30 years. And you see that it's absolutely flat. The way the GPS works on latitude, right? You can convert it to listing. So look at it's absolutely smooth from starting from 1.4, for example. There's hardly any jerk in it. So as if then, it's moving without any jerk, without any, as if it is gliding on the surface, right? Of course, it undergoes seasonal changes because of monsoon. Monsoon is a huge load on Indian subcontinent, and uh, it causes up and down motion of the continent. Why I'm showing this is I'm showing this for a purpose because of these two small creatures which you see at the bottom. Now here what you're seeing here is uh, a smooth motion here which you see uh, for Hyderabad, as if there is a snail which is moving on a surface without any deformation on its body, as if it is simply sliding over it, just gliding over it. But then in contrast, see this caterpillar. So what it does, so because of friction, it holds the ground at the front, holds the ground there because of the structure it has got, and because of surface not fixed. And then it curls up its body and releases. That's how the caterpillar, and that's how exactly the plate motion occurs. So the plate motion, so this is same thing what you see for Hyderabad. This is for a site in Nepal. Oh, I touched it. So you see that on that day in 2015, the site was moving fantastic, very smoothly. But then that day it shifted by this much, just like a meter, and then again started that way. So the motion of curling up takes a lot of time. Strain accumulation, strain accumulation is that's what we call as stick slip motion in earthquake processes. If we can understand, if we can distinguish between the two, right, and if we can understand the motion here, we have, for the students, we have understood elastic rebound theory, we have understood the stick slip motion, we have understood how earthquakes occur in the in the plate boundary. This is, of course, it's perfect. It works fine for plate boundary regions. For plate interior regions, the caterpillar analogy doesn't work. We are still struggling as to how the strain accumulation occurs in the plate interior region. Okay, so this is the map what we have got using all this basic knowledge, all this almost like 20 years of data which we have collected over India. And what you do is you take derivative of it, and you can, since it's a two-dimensional stuff, so you have various estimates of strain. You can see strain in the form of shear strain, you can see it in the form of gravitational strain, or you can see it in as second invariant strain rate. What you see here, you see large strain is over the Himalayan region. That's what you expect, right? You see very low strain going up to almost like 1 to 4 nanostrain per year, which is typical of a stable continental region. In the plate bound region, and the strain goes up to almost like 2 orders up, so like almost like 70 to 100 nanostrain per year in the plate bound region, and in plate interior it generally typical is 1 to 4 nanostrain. But then there are some regions, for example, Kutch, the strain rate is much higher. Strain rate is almost like 10 nanostrain per year. And that's also a reason because of which Kutch region is more productive in terms of earthquakes. We had earthquake in 1819, and in almost like 200 years, there was another earthquake in 2001. So how can a stable continental region, of course it's a failed rift region, how can a stable continental region produce two major earthquake in such quick succession? Where from the strain coming? What is the source for this strain? I agree that failed rift region has got different structures, has got different lithology. It has undergone tremendous tectonics in past, but there must be some supply of energy, strain energy, the region which will be released during such major earthquake. And to understand this, if I slightly change the scale here, get rid of this Himalayan region, and just look at the strain in the stable continent, right? So I have removed the high strain part from it, and now you're seeing only the lower strain which is there in the stable continent. Rescale it, and this is what you see here. That this region here, west of Delhi Ravli, is showing up in high strain rate, high shear strain. The fact is that this region is actually moving slightly slower than the rest of the Indian plate, because of which it is exerting more pressure. Because it is moving slower, it is exerting more pressure on the Kutch Rift, and because of which Kutch Rift is more productive. That's the reason, because of more productivity of Kutch region. That's also a reason because of which Delhi Aravalli belt is keep producing small magnitude earthquakes. And all these earthquakes are, if you look at the focal mechanism of all those earthquakes, it is consistent with the strain rate map, which in terms of direction with this map. So this is strain current deformation. It is able to explain the compression. So far we were struggling that where from the compression comes in the Kutch Rift. And the idea here is that I call it as Rajputana block, east of Delhi Ravli region. I call it as Rajputana block. So Rajputana block is moving slightly slower. It's like 1 to 1.5 millimeter slower than rest of the Indian plate, because of which it causes strike slip motion on the Delhi Ravli fold belt, and also causes huge compression on the Kutch Rift, making both these regions as seismically very productive. Sorry, that's right, sinistral, for sure. Okay, this is to argue that, look, fine, strain map is fantastic, but then it doesn't work. Honestly, it doesn't work, because strain, by definition, it's a derivative of displacement. So a region which is perfectly locked, right? The displacement variation on the top of it not be much, because it's locked, right? The change in deformation occur only the transition where from perfectly locked to perfectly or imperfectly locked, wherever there is transition. So on top of this perfectly locked, fortunately with Himalayan, because we have huge area which is exposed above the perfectly locked catchment, like 100 wide, where that's where the strain would be less. Now, if the strain is less, the common sense would be, if the strain is less, so that means the seismic hazard is less. not correct, right? So strain map cannot be taken blindly. And to further support my argument, this is a plot, slightly tricky one, but what it says is that look, uh, the red curve is a strain curve. So what I have done is I have arranged these strain pixel from increasing to decreasing order, right? And in the same pixel, now I'm looking at number of earthquakes. I'm pixel the same order as from increasing strain in earthquakes, location, topography, and I'm plotting them to all together. So what you see that look, uh, the topography is perfectly matched with the strain. That's what you expect. Topography is the result of partly the result of plate partly. So it is correlated with strain map. It is also correlated with earthquakes. But then look at the population, where the population is placed. The population is oppositely correlated. So the places where strain is high, population is low, and the places where strain is low, the population is high. Strain is low in the frontal part, right, where we have large population. So this map, in a way, is giving slightly tricky. I mean, those who understand, they will be able to correlate the two. Yes, sure, agreed. Agreed, 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 agreed. So that's why I said every map has got its own limitation. It has got its advantage, disadvantage. So we need to understand for what purpose we are looking at it, right? I'm coming to the my locking map actually. So I'm building up the case for why do we require locking map. That's the reason. So uh, so you see that look, the population is not correlated with the is not correlating with the strain rate map. That's what you expect, and that's the reason because of which the locking map comes in the discussion. So what I'm going to show you is one small uh, region, for example, Garhwal Kumaon here in Himalayan region, wherein we have fantastic GPS network, the best network we have anywhere in the Himalayan region, including Nepal. So that's the best network we have. It's like 40 stations we are running in Garhwal Kumaon, and that's how they look like. So uh, this is a beautiful station at Yamunotri, one of the Char Dham, and the map here on the right shows the displacement vector, how it changes from Indo-Gangetic Plain, higher Himalaya. As you move from Indo-Gangetic Plain, motion is zero because I'm considering the motion with respect to India. So the motion is zero on the Indo-Gangetic Plain. And then I start moving towards north, the size of the vector increases. That's what you expect. You expect that uh, if it was not a caterpillar, but if it was a snail, right, then either there was no differential motion or there was sudden change in the motion when the surface was frictionless. But if you see a gradual increase in motion, as if the caterpillar is trying to curl up, right, accumulating strain, that's what you see in this map, and that's what the elastic rebound theory says, that look, uh, you see that it is, we call it a typical S curve, strain curve, that gradual gradual increase in the strain, gradual increase in the displacement vector, and that's what you see in the Himalayan region, in the Garhwal Kumaon region. So if you plot these vector on a profile, right, that's the curve which you will see, uh, and what does it how do you interpret? In a very simple manner, this is what geologists say, that look, uh, in Holocene or in recent time, the total convergence accumulated HFT, main MFT, whatever you call it, is about 20 millimeter per year, 20 per year. So you see that the green curve which you see, that's what the geologists say. That's what those who work on on a long-term deformation, that's what they say. Convergence rate in the Himalayan region is about 2 centimeters per year. And the curve, the black curve which I'm showing, is the curve which you are seeing today, right? So what is the difference? That's the difference. That's the strain, that's the amount slip deficit or the displacement deficit which is occurring in the Himalaya. Displacement deficit or strain deficit is maximum in the frontal part, and as you move towards north, it started earthquake nucleate somewhere here, uh, and then it releases all the strain if the rupture is full, not the partial one. You can now this as I said, it's all built up on plastic rebound theory. You can convert it into slip deficit, you can convert it to locking map, things like all those products. So this is slip deficit, but then this is what you see nowadays in lots of regions, that people are it's becoming very fashionable to show locking map of subduction. And the importance of this is that, look, these locking maps are important because they tell you which are the regions which are strongly coupled, which are the regions where you can have future great earthquake. These are the regions where the strong coupling regions are the regions where the damage would be more in the future earthquake, because slip would be more in those regions if the rupture is full. So that's what you see, such maps all over subduction zones, and that's what we have also done for entire Northwest Himalaya, because that's where we have the best network. Of course, we also have beautiful network in Arunachal, Sikkim, but right now what I'm showing you is a locking map of Northwest Himalaya. It has got I can devote 1 full hour on explaining this map, the intricacies. I see a lot of things here. For example, you see an eye there. So it shows how heterogeneous is the coupling, and it's actually directly related to the topography. That's, by the way, that's the Srinagar Valley. So the region which has got subdued topography is less coupled, and that's what you expect. That's what. Sorry. Oh yes. So you see that here. Earlier one. Yeah. Well, topography is certainly a product of surface processes, geological processes, and plate tectonic processes. And of course, plate tectonic processes dominate, especially in plate bound region, and hence you expect a high correlation between all these quantities. You expect high correlation in earthquake density, topography, locking. You do expect that, certainly. Right. So what you are saying is that here you should have high topography at the front, and then as you move towards north, topography should decrease. Yes. Yes. Right. Right. That's right. Low friction. That's a low friction. In the Srinagar Valley, you have low friction. The valley. Within high topography, you have Peer Panjal on this side, then Scar on that side, and in between you have low-lying area. Has got low friction. Well, overall topography is high, but as compared to Pir Panjal, Janskar, Srinagar topography is certainly, it's a valley, intermountain valley, locally, relatively. That's right. Certainly. See, so that you know, yes, the two things are not directly correlated because buildup of topography uh, involves a lot of other processes also. Erosion is, of course, one of the geological process, but one of the reason. I mean, the fabric of uplift of the plateau. So those things are. What I'm talking is how locking or how the current deformation is related to the topography. It's not that everything can be explained by there's, that everything can be explained by only uh, by elastic strain. No, no, certainly not. Certainly not. We are only looking at one component of mountain building, which is elastic, which is earthquake. Okay. Should I go where? Yeah, yeah. What is? Oh, inflection. Okay. Oh, yes, yes. That's so that inflection corresponds to the place where the strongly coupled MTZ, sorry, MST, main Himalayan thrust, transition to a seismically creeping uh, main Himalayan thrust, MST, main Himalayan thrust, the subsurface. That's almost close to Munsiari, Dharchula, Fulchetti, Oli. Yeah, Oli. That's right. That's right. That's where you have transition. That's MCD, almost like MCD for sure. In our um, understanding, these MCT or MBT, they are there on surface, but at depth, everything is actually controlled by main Himalayan thrust. Yeah, it's just by chance, or may not be by chance, that MCT in this region occupies the place where you have transition from strongly coupled to aseismically coupled. Yeah, it's just. But true, true, true. But elsewhere, if you see elsewhere, if you if you see here, MCT is not exactly follows the transition. MCT is at all places it does not follow the transition. Sometimes it's up, sometimes it's not, sometimes it's south. Yeah, I think I think I need to stop, right? Oh, as you wish, as you wish. As long as you take care of my flight. Thank you. Okay, just to give you a few more slide on how the intraplate deformation occurs, which I also do not understand. But then, as I said, I'm poor in understanding. So whatever I have understood is only through data. I collect a lot of data, and whatever data says, I I put it on the papers. Uh, I know that there are more intelligent people who work with theoretical analog models, right? And they produce fantastic results. But for me, as of now, it's all about data. Collect data and see what data tells. So let me go to the to just two slides to show you how Kutch, for example, if it deforms, and how do you see it? So we have a beautiful network in Kutch region again, which has got almost like S20 S data. And what you see again, you are seeing these vectors in Indian reference frame. And if you see carefully, look at the sites which are located south of Kutch Rift. They're all moving towards north. Look at the sites which are located within the rift or to the north of it. They're all moving towards south, right? Now this is when I saw for the first time 4 or 5 years back, I thought there's something wrong. It cannot be so straightforward. But then we started realizing that this is a real pattern. And earlier we thought that it could be because of the 2001 earthquake has occurred just recently, and it was a large magnitude earthquake, so it must be causing deformation in the region, and that could be causing showing up a pattern like this. So we did the modeling for post-seismic deformation for 2001 Kutch earthquake, see what will be the impact of surface deformation onto it, and then there was absolutely no match. Deformation of Kutch earthquake is long gone. We are in 20 years now, so it continued for 10 years for sure, 5 to 10 years. But then after that, the deformation because of post-seismic deformation of Kutch earthquake was not there. That means whatever we are seeing is because of the compression which is happening across the Kutch Rift. Now, intuitively, that's what you expect. That if you have thrust earthquake, if you have reverse earthquake occurring in Kutch, that means there is some compression going on. But where is the evidence for it? Where is the data for it? And that's what GPS gives you. So GPS, these observations, they showed that yes, you do see the compression in current day tectonics. And if you put them together, if you take a profile here, that's how it looked like. And if you put a model and you apply some compression across it, you are able to simulate these vectors. You're able to simulate the pattern because you have applied compression across this rift. So now, where from this compression comes? That was the question which we are unable to answer at that point of time. But then, because of this entire Indian plate region strain analysis, now we understand that it's the Rajputana block which is slightly moving slower than the rest of the Indian plate, causing compression, Kutch Rift. And hence, you have a large productivity of earthquake in West. Oh, it's very, really early fold belt. Really early fold belt. We do not know to the west because there's no data right in the Pakistan region or there. So, but to the east, it's really early fold. Oh yes, that's a problem. That's again a problem. All these products are dependent on data, and in across Narmada zone, we don't have. We do have some. We do have some sites across Kutch, but not enough to quantify the strain there. But now we have an experiment across Godavari and across Kutch, across Narmada zone, which gives us idea about how these field lifts are deforming. 97 was a small earthquake, I should say 5.6, 5.7 magnitude earthquake. It did. Certainly. But I don't expect that it will show up in the current deformation, or it occurred at a depth of 35 kilometer, very small earthquake of 5.7. These 2001 Goja earthquake was 7.7, 7.6, several, probably 100 times or more than 100 times stronger than the Jabalpur earthquake. I'm so sorry. In 2015? Oh, yes, of course. Ah, another lecture. Uh, 2000. No. I'm saying. I mean, yes. 2015 earthquake is special. It's special in the sense that number one, partial rupture. The rupture did not propagate to the south. Number two, that's a new avenue which we are now going into by not by just looking at the static deformation, but also looking at dynamic displacement. What exactly happens when earthquake occurs? How do the particle moves? When the earthquake is occurring. Oh yes, of course. Yes, of course. And not we, but of course, people did record, and that was the evidence that if you look at the damage in Kathmandu Valley, it was limited to certain structures. And it was limited to certain structures because the natural frequency of those structures matched with the natural frequencies of waveform which was released by the earthquake. So there was resonance, and that came out only because we had 2 GPS stations in Kathmandu Valley, which actually recorded the dynamic displacement. So it showed the predominance of 2 second, 2 second, waveform with 2 second period. And so all structures which had 2 second natural frequency, they all came down. That's a new avenue which all of us we are looking at. It's also relevant in case of Indo-Gangetic Plains, all cities in Indo-Gangetic Plains, or including Calcutta. That's a new subject which all of us we are entering. I have a small clip on it, but anyway. Yeah. So that's the picture which I always try to sort of just to make sure that everybody is awake. So we do have these. I mean, if those who have understood the caterpillar and snail, movement, then we have all these places which are accumulating strain, right? Remember the Himalayan region, right? So all these caterpillars sitting there, all the places South India being smoothly. Of course, you do have hidden caterpillars sitting here and there, but then motion is largely smooth. Of course, there's no place on any plate which doesn't have earthquake. In time or in next 100 years, 1,000 years, million years, every place will have earthquake. But the whole idea is that how frequent it is. Stable continental region will have less earthquakes, and then plate-bound regions will have more earthquakes. So I think I had a yes. This is one slide which I wanted to show that look, using GPS you can do a lot of other things also. For example, the image which you are seeing here is a grace image. Yeah, the grace image which shows negative anomaly here, where those are in groundwater hydrology. They know that this area is a region where a lot of pumping has been done, because of which this region is experiencing anomaly, which shows up in grays. And look, if you look at the GPS data, all these places are showing uplift. So because of unloading, now the land is coming up. So now Survey of India has got fantastic network in this region, and we have improved the resolution of it, and you can clearly see that which are the regions where the effect of groundwater withdrawal is more prominent as compared to others. It has got strong implications towards agriculture, in the sense that if you continue doing it, then there will be time when pores will actually get collapsed, and there will be no storage of water, further storage, and that region will become barren forever. So, it's important that to do mitigations towards it, so that further pumping is stopped, so that otherwise will destroy the aquifer forever. You can also see how the water moves, water on ground, water subsurface. How does it move annually during the monsoon? Look at here. So this has helped in identifying that where is the hydrological load concentrated on Indian plate. So hydrological load is concentrated here, which is, of course, everybody knows, Indo-Gangetic plain. And then this was a surprise to us. All this hydrological load annually, it all moves towards this region, area, right? So that's where you have high potential of water, groundwater on the Indian subcontinent. It also helps doing a lot of other things by looking at how these earthquakes, they cause anospheric anomaly. Those who are into geology, that Myanmar earthquake was a super shear earthquake, which the speed was more than the speed of Rayleigh waves, speed of shear waves, and hence called super shear earthquake. Super shear earthquakes cause a lot of damage as compared to the normal earthquake or subshear. That's why it's important to know which are the regions where super shear earthquakes can occur. So this GPS again helps you in understanding the nature of these earthquakes. This is the work which we are trying to do now using GPS as seismometer. Right? We saw it in case of the earthquake that how certain structures were damaged because of predominance of natural frequency in the seismic waveform. So you can use the dynamic deformation and do whatever you want the way seismologists, they use seismometers. So now we have started using GNSS as seismometer, and this is one example. So we have a beautiful network in Andaman Nicobar, and there was an earthquake here in Great Nicobar. This was in July 2025, and you see a good match between. So you do the same thing what you do in seismology and estimate the focal mechanism. You can do the same thing here. So by using the displacement GPS displacement time history, you can do the fault plane solution and do the same thing what you do in seismology. So these are some extra thing which we all do. And thanks everybody. Because as I said that it takes all places over continent, exotic places, some scary place. Here, this is Mizoram. How many places? She's Bachendri Paul. It happened that the station which we established, that land actually belonged to Bachendri Paul. So when she learned that we have set up a station, and she came, was spent a lot of time with. Thanks. Oh yes, of course, sir. Of course. So when he was Vice Chancellor Assam University Silchar, that's when we approached him, and he kindly agreed to set up a permanent GPS station at Silchar, Assam University, and it's still working. I'm sure one of the vector belongs to Assam University here. Yeah, and of course we ran into audit objection for it because Assam University did not ask the remaining money, right? So the money which was allocated for this and the money which was paid, so there was a mismatch, right? Thank you, sir. Thank you very much.
Thank you very much, sir, for such an insightful and enriching lecture. We shall now move on to the question answer session. If any. Okay. Yes.
Scared of-
Excellent talk, sir. So fortunate to be listening from you. So one thing regarding, I just want your comment. So you talked about hazard assessment and all that. So most of the earthquakes that we see actually happen at about 10 to 15 kilometer depth. But we are seeing the surface deformation. And in actual, when we do modeling,
Yeah.
we see that the faults actually generate from depth.
Yeah.
And before it actually comes to the surface, when we map the strain in the horizontal upper surface, it shows no negative divergence or dilation. So, but the thrust actually starts being active quite earlier. So, when we talk about hazard assessment in terms of today's horizontal velocity field upper surface, are we not lagging behind about, like, earthquake can still happen at 10 kilometer depth, but we are not seeing that deformation in the surface?
That's not limited. The two. One is whether the surface observer see what is happening, but all of us the same. Or through it. We have been sample work, record earthquake model, try to map the distribution. We have been clearly as far as things can modeling, go to subset and can do the slip distribution modeling at depth. That's um, but that's where importance. Just by looking at data is not a good idea. That's what has been done previously also, that, for example, seismic zoning map of India, it's all based on only on data, historical data. No physics-based model has been used. And that's where physics-based models are important. Yeah.
Thank you, sir.
Oh, yes. Yeah. Out of syllabus?
Because since there is one revision, and that has been reversed again,
Yeah.
of the seismic zoning map of India, what extra you have considered while formulating that zone 6? What extra parameters?
If you ask me, that revision was good actually. That revision was certainly good because if you look at this map, Now, what does this map show? It actually, if you look at Himalayan region, you see a high seismic zone here, which corresponds to 1905 earthquake, I guess. This is corresponding to earthquake activity in Dharchula. So just because, there are historical evidence of earthquake occurrence, you have colored them red, right? Now, when GPS is telling, when all seismologists are telling that there is strain accumulation going on all through the Himalayan belt, it's only a matter of time that when the next earthquake will occur. How much justified it is to say that the region intervening between the two is less hazardous than the region adjacent to it, right? That's not justified for sure as far as the data are concerned, as far as the physics-based model are concerned, as far as our understanding of Himalayan earthquake process is concerned. So that's what these people they did, that they understood the process of strain accumulation in the Himalayan region, and that's why they colored the entire region as red. So in that way it was justified just by, one of the problem with all, including seismologists, is that just because it has not occurred in my lifetime, it will not occur in future. Certainly a bad idea, certainly a stupid idea, I would say. I mean, all these earthquakes, all these geological processes, including earthquake, these are, have recurrence interval of sometimes 100 or sometimes 1,000 years. So just because it has not, just because I have not died so far, it doesn't mean that I will not die, right? I will die for sure. Just because I have not experienced an accident, and hence the accident will not occur, and hence I will not wear the helmet, certainly not a good idea. So that's the problem with many seismologists in India especially, that just because it has not occurred, oh, you are saying that in Garhwal Kumaon earthquake is going to occur, it has not occurred even now. So that means the strain is leaking somewhere. That's a very, very stupid idea.
That means you are telling that GPS data was considered to.
I would say the entire process was considered. Okay. The process of strain accumulation, our understanding, honestly speaking, our understanding of Himalayan earthquake has increased tremendously in last 20 years, right? So if you are still 20 years behind, I mean, then what is it which we can say?
Because last revision was done in 2000, after 2001 earthquake, I think.
Yes, that's the problem, that if you only wait for earthquake to occur and then you revise the, so then what science you are doing? I mean, there's no science involved in it, right? Yeah. Yeah. It's counterintuitive. It's counterintuitive that I would color it yellow rather than coloring it red.
Thank you, sir. This brings us to the end of today's session. On behalf of Geological Institute and the Department of Geology, Presidency University, I extend our heartfelt gratitude to Dr. Vineet Kumar Gahalaut for delivering this wonderful memorial lecture. We are also deeply thankful to our respected faculty members, alumni, students, and guests for their gracious presence and continued support. Finally, I would like to express our sincere gratitude to the authorities of Presidency University, the Department of Geology, and all the staff members for their constant support and guidance in making this event successful. I would like to request everyone to kindly join us for refreshments arranged outside the auditorium. Thank you, everyone.